Hi, welcome to the new section on algorithms and data structures. So in this section, I'm going to talk about the heap trees and how we can able to demonstrate two important heap algorithms. So this presentation is mainly concentrate on the logical overview of how we can able to do two types of insertion and deletion, that is percolate up and percolate down. How we can able to insert the elements in an orderly way. So let's go and deep dive. So in this section I'm going to discuss about what is heap and what are the elements in a heap and how we can able to arrange the elements in a heap and what are the properties of heap and when do you say it's a heap or not. So in heap is nothing but a certain kind of complete binary tree. So in order to understand what is a complete binary tree and full binary tree, let us see few examples of complete binary tree and full binary tree. So let me just take so here in this one, what is the definition says? A complete binary tree is a binary tree in which every level except possibly the last level is completely filled and all the nodes are as far as left as far as possible. So what do I mean is, like, if you see in this tree, all the levels are completely filled. Like if you see the first 0th level, first level and the last level, there is an exception to this thing, except possibly the last level. Last level needs not to be completely filled, but they should be left as far as possible. So all the nodes like 4, 5, 6, they are in the left way. And let us see what is a full binary tree. A full tree is nothing but in which each node is either a leaf node or possess exactly two child nodes. So in which each node is either a leaf node, so it's a leaf node, or possess exactly two child nodes. So see, suppose the root 2 is having two child nodes 2 and 2 and 3, and for exactly the root node 3, the child node 3 is having two childs 4 and 5, and for 5 it has two nodes. So if you see in this diagram, in the third diagram, it has one right child 2. So I'm just asking this question: is it a complete binary tree or a full tree? Like, what is the condition for a complete binary tree? A complete binary tree is a tree. All the levels must be filled except possibly the last level. It needs not to be completely filled, but the nodes must be left as far as possible. And the full binary tree is nothing but it should have exactly two child nodes, see, one doesn't have a two child nodes, so not a complete binary, not a full binary tree, and the nodes 1 is not completely filled. The levels are not completely filled, and also the node is exactly on the right, so it's neither a complete tree nor a full tree. So that is what the complete binary tree is. So when a complete binary tree is built, its first node must be root. So how we can able to start the building of the elements? First node is to the root, and then it has two childs. One is left child, then it comes the left child. How we are building the heap? Then it comes the right child. Then for the left child, it will build two childs. The third node is always the right. Next node always fills it should come the root, and it should come from the left to right. When you are trying to take an elements, like if I have the set of elements, like if I have 4, 15, 13 like that, always it should start from the root and from the left hand, and then it goes to the right hand. And for the left child, it should have two childs, and for the right child, it should have two childs right node. So it should start from the left hand to the right side. So that is what the heap is. And this is a complete tree because all the nodes, if you see, they are completely filled in each level, and it's like you can see, each node in a heap contains a key that can be compared to other nodes. And the other heap property is max heap. So what is a max heap? Max heap is nothing but the elements in the parent node, the elements for the parent node must be greater than its child key. So if you see the 45, out of all these nodes, out of all these childs, which is it having, it is greater than its child. Then we'll take another subtree. So I'll just take. So first I will take this subtree. (35, 27 and 21). you don't need to, this is not a binary search, you don't need to find the left one is smaller or right one is bigger or something like that. The condition for the heap order property is you should the parent should be greater than the left and than its child's. Here also if you see 23, 22 and 24, 4, the parent is greater. Here the parent is greater. And if you see the whole tree, the 45 is greater than its child nodes. So that's what the basic property. Here also we can see another tree. So 27 is greater. So this is a heap order property. So it should satisfy the heap. It should satisfy two conditions. One is it should be a complete binary tree, and it should satisfy the max heap property. The max heap property is nothing but the parent node should be greater than its child, than its left child or than its child's. So that's what the heap property is. Let me just erase. So the heap property requires that each node key is greater than or equal to the keys of its children. So what are the keys that are there? It should be greater than or it should be equal to the keys of its children. So normally it should be greater. So if I'm adding a node to the heap, suppose if you want to add any element to the existing tree, you should start it from the ending. Like I should start it from here, and I can put a node and put any element that you want to insert. So this is what the insertion starts. If you want any other element, you should put to a left side here and the right side here. I think let me just change it. So left, right. So that's what the insertion goes on. So now I am putting 42. But if you compare this tree, 42 is bigger. So you have to swap the elements. 27 will come here and 42 will go here. Because the heap order property says that always the parent should be greater. Then it satisfies the heap. Next we will see this tree. So that's what you see. You should see each and every subtree. If it satisfies the heap property or not. When you put 42 here, again 42 is greater than 35. So you should swap these elements. 42 should be coming here. And then if you compare 42, 23 and 45, the heap property says. So that's what. Here 42 comes here first and then 35 comes here. So 35 will be swapped with the 42 element. So you should when you are inserting the elements, you should swap the elements by going up. So that's why we call this swapping the elements and going up is called percolate down. That's why we call adding a node to the heap is nothing but inserting an element to the heap tree. So we call this percolate up, and the algorithm is also there. I'll try to explain the algorithm, all the algorithms related to the trees and related to the AVL trees and everything in the programming lab section. So let me just erase these things. So you can see, put the new node in the next available spot and push the new node upwards and swapping with its parent until the new node reaches an acceptable location. An acceptable location is nothing but it should satisfy heap order property, and the heap order property says that always the parent should be greater than or equal to the child. So 42 is being replaced here because the parent 42, because always the parent should be greater, and then we will try to compare this tree. This tree, it should be swapped with 35. So 35 comes down, and this tree, it's complete binary. It's a complete binary tree. So it satisfies because every node, every level is completely filled, and also all the nodes are in the leftmost position except the last level. They are not completely filled, and that's an exception to the complete binary tree, and also it satisfies heap order property. So then parent as a key that is greater than or equal to the node, or the node reaches the root. So that's what the node, it should reach to the root. Always it should satisfy the heap order property. So the process of pushing the new node upward is called percolate up, and this is also called inserting an element, a new element in a heap tree. If you want to insert the elements, you should it's called percolate up. Now we'll see how we can able to delete the elements from the heap tree. Suppose I want to delete and I want to put 45 in an array. So I want to delete the elements one by one. So first element I want to delete it. First you need to go 45. So first you need to remove root. Then after removal of root, you should swap this 27 with the new empty element that is because it's being removed. You should swap it here. Once you swap, the heap order property you should see, because you are putting 27 here, and you should and this element becomes null, empty, and there won't be any elements. And then you should try to see 35 19, it's good. 23 22 24, parent is greater. You should see the heap order property is there or not. And 42 35 21, it's there. But for this 27, you should see 27 42 and 23. The 42 should go here. Let me just erase everything. And then 27 will go up. Push the out of place node downward, swapping with its larger child until the new node reaches an acceptable location. So we should compare and we should make sure that it satisfies the heap order property. So 27 is being replaced by 42. So here you can see, but here 35 should be replaced with 27, because in the heap order property parent should be greater. So 35 is good, 23 is good, 42 is good. So this is a heap. We are just going down, that's why it's called percolate down. So the children all have the keys less than or equal to out of the place node. So all the children nodes, all the child nodes should be smaller than the parent, and the node reaches the leaf. The process of pushing the new node downward is called percolate down, because we are coming down. So we are swapping the elements and pushing it down until it reaches to an acceptable location. That's called the percolate down. And now we'll try to see how we can able to an array of day. So always the array starts with 1, 2, array starts with 1, and the index starts it from 0, 4, 5. So the elements that you need to be coming is 42, 35, 23, 27 and 21. So always the root, left, right, left child, right child, and the new child that is going to come is the left side and the right child. So that's how you need to construct an heap, and that's how you need to insert a new element into the heap by putting on the left side and right side position, and you should satisfy the heap order property. And we don't care what's this part of the array is like this. And important points about the implementation is the links between the trees are actually not stored as pointers in another way. The only way we know that the array is a tree is that how we manipulate them, the way we manipulate the data. So now this is the array implementation of the heap. So array implementation starts always the root, left child and right child, and for the left child whatever the childs it has to start like this. So that's why we have the heap. If you know the index of a node, that's easy to figure out how the index of the node is parent or children, and you can just see the refer the textbook if you need anything. So this is a summary. A heap is a complete binary tree where the entry at each node is greater than or equal to the entries of its children. So the parent should be greater. To add an entry to the place a new entry at the next available spot and perform a reheapification upward. So it's nothing but percolate up. To remove so in order to delete an element from the heap, move the last node onto the root and perform a reheapification downwards. Nothing but percolate down. So this is what the heap trees, and this is what the max heap, and what are the properties of heap trees, and we have seen how to insert an element into the heap and how to delete an element from the heap. So you have to so if there is any kind of question, do let me know, do post it in the comments. And thank you for watching the video. Have a nice day. Take care.